Conditional probability. Here's an outline. We'll define conditional probability. We'll look at a couple of tools for determining them and depicting. We have data in tables and tree diagrams. That's also going to give rise to another concept known as independence. And this can occur when we have selection with and without replacement, and we'll look at some examples. So sometimes a priori knowledge about a situation can influence probabilities of events. For example, if you know it's cloudy, you can estimate the probability of rain to be greater than if you didn't know it was cloudy. Knowing that a group of individuals is smokers tells you something about the likelihood that they'll develop cancer. So these are called conditional probabilities. We say the conditional probability of B given A, and this is the way it's denoted, and note that the assumed event is to the right of the vertical bar. So again, we assume that event A has occurred. So the conditional probability of rain, given that it's cloudy, would be written this way. We assume that it's cloudy out. Okay? Here's an example with M&Ms, selected one at a time. So you're at the movies, you can't see them, so it's a random selection, and you're eating them, so you're not replacing them. So the probability of getting red, well, there are 11 total and there are 4 red. Equally likely outcomes approach. Now, suppose you've selected a red, then there are 10 left, and 7 of them are still green. So the probability of getting a green, given that you've gotten a red on the first one, is 7 out of 10. So the event selected red on the first influenced the probability of getting a green. Okay, so now if you condition the other way around, or you assume that you had a green on the first, right? Now there are still 10 left, but all of the red are still there. So that probability is 4 out of 10. Okay, so you can see if we condition one way versus the other, the probabilities are not in generally going to be equal. We can depict this situation using a tree diagram. Here we have our first selection represented and then our second selections, and we can write down the probabilities on the branches. So this is the probability of red on the first, and this is the probability of green on the second, given red on the first. We said that we've selected those M&Ms without replacement, pretty obvious reason. We ate them. If we selected them with replacement, well, we'd have different probabilities. Here's a similar example, but we'll use balls in this case. So the probability of red on the first selection, same as before, 4 out of 11. Now we've replaced that red ball, so the probability of green, given that we got red on the first, is 7 out of 11. And that's the same no matter what happened on the first. So the probability of green on the second selection is always going to be 7 out of 11 because we've made the selections with replacement. We say that 2 events are independent if one having occurred doesn't affect the probability of the other. So in this case, the green on the second and the red on the first are independent. Red on the first does not influence. Otherwise, we say they are dependent. Here's how the notation works. So if B having occurred does not influence the probability of A, we say A and B are independent. So classic example is coin tosses. Doesn't matter if you flip 10 heads in a row, the probability of heads on your 11th toss is still a half. Here's an example using right from our text. Sometimes you can read these conditional probabilities right off of chart if you're given that. So we can see from the chart that the probability that a person uses drugs is 50 out of 555. There are 50 drug users out of a total of 555. We can also look at the probability that a person tested positive, which is going to look at the positive results. There are 70 out of 555. So now you ask the question, an employee tests positive, what's the probability that they're actually a drug user and this not just a false positive? So we want the probability uses drugs given that the test is positive. So given that the test is positive, we're in this situation here. There are 70 total positives and 45 are users. So 45 out of 70. So about 64%. So given that the test is positive, about 64% chance person actually uses. Well, that means about 36% false positive. That's not so good, especially if it's you who just failed the drug test. Now, suppose the company that manufactured the test claimed that it correctly identified presence of drugs 92% of the time. Were they lying? Well, correct identification of the drug's presence would be the conditioning the other way. So that would be assuming that there's drug use, the test is positive. So that would be correct identification of the presence of drugs. That's what they're claiming. Well, let's look at our table. So we would look under the drug users row here, and we'd see how many positive results, 45 results out of 50 total. So you'd get that conditional probability is 45 out of 50, or 90%. So really the company didn't lie. They're pretty close. They claim 90% and or 92%. So as you can see, we need to be very careful when using conditional probabilities. And in particular, what event is being conditioned on, what is being assumed. And in certain situations, the probabilities can be very different. For example, if you have very low probabilities, in the case of rare diseases, for example. And it's also famously, physicians and lawyers confuse these concepts. So to summarize, we've looked at the conditional probability of B given A, where we assume A has occurred. We looked at a tree diagram to depict these probabilities and outcomes, and we also found conditional probabilities from a table with our drug test example. We looked at independent events where probability of one having occurred doesn't affect the probability of the other. Coin flips were a prototype example. And also if we're making selections with replacement. So if we're making selections with replacement, the outcomes are independent. If it's without replacement, we saw that they can be dependent. The multiplication rule will wait until the next video. So stay tuned.